Hi, in previous lecture I discussed transitive closure by using Borsal algorithm. There we check whether path exists or not. If path exists, then it is 1. If no path exists, then it is 0. In today's lecture I will discuss all pair shortest path. We will use the same concept of finding transitive closure. So first go through that lecture and come to this lecture. In all pair shortest path, we find shortest path from each vertex to each other vertex. We can also solve all pair shortest path problem by single source shortest path problem. We can consider all vertex as source. If edge weights are non-negative, then we can use Dijkstra algorithm. We will consider every vertex as source. For Dijkstra algorithm, running time is order of b square if mean priority queue is implemented as linear array, and its order of e log v if it is implemented as binary min heap. So if we use Dijkstra algorithm for finding all pair shortest path, then for one source this is the running time for b source. So if we consider all vertex as source, then running time will be order of bq, here order of v, then number of edges log number of vertices. So this is all about greedy technique. We can also use dynamic programming for finding all pair shortest path. We can use Floyd's algorithm. It's called Floyd's algorithm after its co-inventor Robert W. Floyd, or simply you can say Floyd's Warsaw algorithm. It's applicable to both undirected and directed weighted graph provided there should not be any negative weight cycle. It is convenient to maintain the length of the shortest path in an n cross n matrix called as distance matrix. So we defined Dij power k recursively. Dij power k equals to mean of Dij k minus 1. So in previous, what is value of Dij, or Dik k minus 1 plus Dkj k minus 1. So whatever is minimum from these two, that will consider as a path. For k greater than equals to 1 and Dij power 0 equals to Wij. So the idea of Floyd's algorithm is whichever path is shortest, either this Dij k minus 1 or I to k and k to j, whichever is shortest, that will consider as a path. Suppose this is 6 and this is 2 plus 3 5, then we'll consider this path, whichever is shortest. Let's discuss Floyd's algorithm. One weighted matrix is given. So here input is the weight matrix W of graph with no negative length cycle, and output will be the distance matrix with the shortest path length. D power 0 will be W, that is the weighted matrix. Then for k 1 to n, for I 1 to n, for j 1 to n, then d power k ij will be minimum d power k minus 1 ij, or d power k minus 1 I to k plus d power k minus 1 k to j. So from these two, which one is the minimum? That will be distance, and we will return d power n. There are three nested for loop, that's a running time will be theta of nq. Let's discuss one example of Floyd's algorithm. One directed weighted graph is given. So weighted matrix will be D0. In D0 we'll write weighted matrix. From A there is out degree to C and cost is 3. So A to C weight is 3. Then B to A weight is 2. Then C to D weight is 1, C to B weight is 7, D to A weight is 6. And weights to itself is 0. A to A is 0, B to B is 0, C to C is 0, and D to D is 0. And which weights are not defined, these are infinite. Next we'll find D1. For D1, we'll mark first row and first column. We are checking is there any path via A row and A column will mark. So B to A weight is 2, A to C weight is 3. So B to C weight will be 5. B to A 2, A to C 3. So B to C cost will be 2 plus 3 5. Previously it was infinite, now it will be 5. D to A cost is 6, then A to C cost is 3. So D to 6 cost will be 6 plus 3, 9. Only these two costs will be changed. One is 5, another is 9. Next, for D2, we'll mark second row and second column. So is there any path via B? That we'll check now. So C to A, 7 plus 2, there will be path 9. C to B is 7, B to A is 2. So this cost will be 9. Only this weight will be changed. Next, we will find D3. So, we will mark third row, third column. We are checking is there any path via C. If we will check via C, A to D, there is a path. A to B, there is a path via C. So, this D value was infinite before. Now, it will be 3 plus 1. It will be 4. So, A to D cost is 4. Next, A to B. So, A to C 3, then C to B 7. 3 plus 7 is 10. Now check D to B. Previously it was infinite. Now it will be 7 plus 9. It will be 16. So, D to C, it's 9. 6 plus 3. Then C to B, it's 7. So, D to B, there is a path D to A to C, C to B. This is 6, 3, 7. So, 9 plus 7, it will be 16. We found D3. Next, we will find D4. For D4, we will mark 4th row and 4th column. We are checking is there any path via D. So there is a path from C to A via D. C to D, then D to A. So it is 6 plus 1 is 7. So C to A cost was 9. Now it will be 6 plus 1, it will be 7. No other path via D. So just C to A value will change, it will be 7. In this graph, there are 4 vertices, so n equals to 4. We found D4. So this D4 is the distance matrix from which we can find shortest path to each vertex. So A to B shortest path cost is 10. A to C, then C to B. 3 plus 7 it's 10. A to C shortest path cost is 3 direct. Then A to D it's 4. A to C, then C to D. So 3 plus 1 is 4. So like this, there is shortest path from each vertices to all other vertices. In today's lecture, I discussed Floyd's algorithm with one example. In next lecture, I will discuss one more example of all pair shortest path. If this lecture is helpful for you, please like, share and subscribe. Thank you.